Hi everybody, and welcome to the first webinar of the new year. As Jed is uploading his presentation, just a few introductory remarks. Again, the overall aim of the CIG Webinar series is to connect mathematicians to computer scientists to geoscientists, among others. The presentations in the series will be approximately 45 minutes in length, with questions and answers following during the remaining time. These webinars are being recorded and will be available for on-demand viewing through geodynamics.org as well as through our YouTube site. Only the host and presenter will have their microphones enabled, so use the chat window to type in your questions or to communicate with others. There's also a slight delay in the audio and video feed, so please be patient as we hand off the presentation. So today we have Jed Brown, who's a postdoctoral fellow at Argonne National Lab. Jed received his Ph.D. from ETH in Zurich in the glaciology group. Jed is a PETSC expert, having given a number of tutorials on PETSC,
can you hear me all right?
Which stands for the Portable Extensible Toolkit for Scientific Computing. His research emphasizes robust and high-performance parallel software and spans topics from ice sheet modeling to computational fluid dynamic modeling of airflow for DC motors to numerical methods such as scalable solvers for nonlinear equations and high-order PDE discretization.
All right, I guess I'll just start right in.
Today, Jed will be talking about.
All right, I guess I'll just start right in. Yeah, I'm going to start out at a reasonably elementary level and lay out the reason why we need implicit solvers. Look at some common attributes that different classes have. Then I'll go on to certain ways that the solvers can break down and what kind of approaches you might want to pursue when figuring out why it's breaking down and how to fix it. Then I'll talk about coupling approaches for multiphysics systems, a little bit specifically on Stokes problems, and then a couple notes on performance. And hopefully I'll get that into this period. If you have any questions, please just ask. It's totally fine for me to take care of it during the talk, so speak up. So looking at the role of implicit solvers, why do we need solvers at all? Why can't we just use explicit methods? Well, the reason for that is called stiffness. So we would call a discretized PDE stiff if the true physics is propagating information much more than one grid cell over a time step length that would be desirable for the transient dynamics. So if information doesn't really move that fast in the physical system we're trying to approximate, then we don't need an implicit solver at all. So if I take some fluid dynamics equations here, I'm leaving out temperature, and I look at, I can't tell a priori whether this system is going to be stiff or not, but I can go and look at the regime that I'm in, and so I might say that it's close to incompressible, or at least it's a low Mach number, so the acoustic wave travels a lot faster than, say, a mantle or lithosphere timescale. That's going to make this time derivative effectively small, and now I get anelastic equations. So this is now a constraint. That's going to involve a piece that I have to solve, but it allows me to step over this fast time scale. Then we might say, now the regime that we're in allows me to drop this other term. This comes from the Reynolds number being low. This is actually unrelated to stiffness. There's not an inherent time scale that's we're dealing with here. And then maybe we can drop this time derivative on the momentum term as well. And now we get something that looks like a reasonably familiar Stokes-like system. We might make further approximations here, but here we have this system of implicit, in general, nonlinear equations that we have to solve. That ends up being important because at large scale, as we increase our resolution, as we use more processes, we find that the solver ends up taking a lot of the time. Now there's a kind of deep reason for this. If the physics, let's say, that involves the discretization and the expression of whatever physical process you want to solve, in general, if that doesn't scale optimally, then it's a data structure problem. It's not that there's some very deep connection that hasn't been made. It's just the inappropriate data structures are being used. If you get the data structures right, that should all work out and essentially be optimal or within a logarithmic factor or so of optimal. On the other hand, the solver needs kind of deep insight and its open problems in many, many domains to get a solver that really scales as O of n. So we try to get it as close as possible. And also, as we parallelize, we would like nearly optimal efficiency. And again, the solver, it needs to effect an operation that looks like an all-to-all communication. And in that process, doing that with much less work than n squared, we had to do something clever to get there. So I'll look at a few common methods now. When we evaluate methods, we're going to find that they depend on the grid resolution and also on the model parameters. We rarely have methods that are completely independent of both. So we can be a little bit more precise about what we mean for a method to be good. So we'll call it scalable, or maybe optimal, if its performance is independent of the resolution and the degree of parallelism. And we can be finer there and say there's weak scalability and strong scalability. But the basic idea here is we have a reasonably stable description of a problem that we want to solve, and we increase the resolution somehow or increase the parallelism, and we want, say, the iteration counts and the time to solution to behave in the way that we would expect from a naive analysis, to not have a lot of overhead in that process. We'll call it robust if the performance is roughly independent of the model parameters. So this can be the variation in coefficients, it can be the strength of a nonlinearity, it can be advection versus diffusion type processes. And we'll call it efficient, and this is really what we're after, if it solves the problem in a time that's, say, a small multiple of the cost to evaluate a residual. And often we'll settle for it being as fast as the best known method, and we might call that efficient. But our quest is really for efficient solvers. It's very easy to make something scalable. You just make it really slow in all cases, and all the overheads will go away. The problem is when you make it efficient, that's hard. So we'll look a bit at linear problems. Most of the time, I think in our applications, the linear problems are arising from linearizing some nonlinear system. That step isn't necessary, but it's convenient for reusing software, it's convenient for debugging, and sometimes those are among the most efficient methods to solve the nonlinear problems as well. But we'll look at a couple examples where we can skip that step. We can break solvers into a few different classes. So maybe the first decision that we might make is whether we do a global linearization or not. So a global linearization is often a Picard type method or a Newton linearization. And in general, we can write these like solving for some defect. So we can take some matrix, I call it J here because in a Newton method it's the Jacobian, but that's not really necessary. And we end up solving a system like this for some step W, where f is the residual of the equation that we wanted to solve. So we wanted to solve f of u equals 0. So the next decision that we'll end up making is between direct methods. Typically those take advantage of sparsity, but direct methods versus iterative methods, which typically involve preconditioning. And among preconditioners, there's classical relaxation methods, there's incomplete factorization, there's actually a bunch more exotic methods that are kind of related to that family. And then there's domain decomposition and multigrid methods, which eventually become very closely related. The other aspect in the global linearization is some kind of globalization process. So this is often a line search or a trust region or a continuation of some sort. So we can choose some parameter and we start out in a regime that's say close to linear so that we can solve it reliably, and then adjust that parameter. And there's a bunch of different kinds of continuations. The other track is to avoid any global linearization. And with these methods, they have less setup, because the global linearization, the process of linearizing takes some effort. And then after everything is set up, you still have the issue that when you do a global linearization, it may end up taking more steps because a nonlinearity is activated in one part of the domain, and that may slow down convergence in a different part. So there are inherently nonlinear methods, like the nonlinear GM-res, nonlinear conjugate gradients. Those can use a nonlinear preconditioning. I'm not going to elaborate a lot on how that works, but they can be accelerated similarly to linear methods. There's also nonlinear domain decomposition. And the best of those methods kind of combine a global coarse problem, and they may use a Newton-type linearization on a modified problem, but all of the work ends up happening in local subdomain solves. And there's also nonlinear multigrid, which is closely related. And typically the name there is the full approximation scheme. So these methods highlighted in red, these can be scalable. Essentially all the other methods here, right, globalization is not a competitor to linear solves, they're related. But all the other methods here can't really be scalable in the sense that we discussed earlier. It's not a methodology that's amenable to that. When evaluating which track to go with, we can look at how nonlinear the problem is at different resolutions. So if we think of some homogenized coarse problem, is that nearly linear? That is the long-range coupling close to a linear process? Or is that a very nonlinear process? And also, how expensive is the setup? If we're going to choose to linearize, do we have to assemble everything? Is that going to be very expensive or not? So those are going to guide choices about whether to use global linearization or whether to stick with a nonlinear method. Now, I'm not really going to consider direct solvers here. The reason, kind of as I mentioned earlier, is that the direct solvers really do not scale. So the slope of a line like this is much, much more than 1. And in fact, as we parallelize, it doesn't, it ends up not scaling very well. So direct solvers are really good debugging tools. They're really good for relatively small problems, especially in 2D. As you go to 3D models and high resolution models, it really is not a viable approach. The same largely applies to incomplete factorization and one-level domain decomposition. In these elliptic problems that we end up dealing with that have relatively strong coupling over large spatial distances, the one-level domain decomposition also really do not scale. But they can still be fairly practical because the cost per iteration is not very high. So, so sometimes they're a good choice, but it's never an efficient choice. So for direct solvers, the memory usage, particularly in 3D, ends up being a serious bottleneck. So we'll focus on iterative methods. So to start out with linear methods, I'll define a matrix. And the reason here is because I have a very general interpretation of what a matrix is and what we can apply a linear solver to. So it's just a linear transformation. We're not going to assume more structure. Now, sometimes we'll form or assemble a matrix, and that basically means to define its action in terms of entries. Assembling matrices is really useful, but there's lots of systems that we'll end up working with, we'll treat as linear operators, use a lot of our infrastructure without ever assembling. So this is a bunch of examples of linear operators. And it turns out a bunch of these are dense. We can still work with them. They have a lot of structure. In many cases, we can apply them, solve with them, and solve eigenproblems with them, all in optimal time, O of n time. But they're dense, and so if we were to form them, it would be immediately at least n squared. Other systems are not very sparse, and so it's beneficial to not form them either. So for the purposes of computing, all of these matrices don't have entries. They do in principle, but we're not going to represent them that way on the machine. If we have a matrix without entries and we want to do something with it, most of our methods are one way or another built on Krylov subspace methods. So here we take some original linear system, or at least an original vector, and we apply the operator to it multiple times. The details here are not really important, but we're looking for a well-behaved spectrum, either in terms of the eigenvalues or the singular values somehow being clustered. If we have that kind of property, of which for a symmetric problem especially, it's nicely captured in the condition number, symmetric positive definite problem. If we have that property, then we'll find that methods end up converging very fast. There's some interesting counterexamples that will make you want to choose different Krylov methods, but GMRes ends up being a very reliable kind of standard, and often we'll experiment with methods using GMRes, and then we may switch to other somewhat preferable methods once we've figured out the behavior of the system. So typically we can apply the operator in some optimal amount of effort. And in the case of GMRes, as we do more iterations, there's a little bit more work here. Normally the constant associated with this is quite a bit smaller than the constant associated with this. So there's a crossover point at, say, n of around 50, for example. So I'll work a little bit with a model problem here. I would encourage people to experiment more with this. So it's in the PETSC repository. This is a scalar problem, but it has a lot of features in common with some of our vector problems. And so it's easier to understand the behavior. And really the important nonlinearity here is this P Laplacian part, for which we'll typically regularize, but this is going to end up looking like variable coefficients. The eta here is nonlinear in grad U through this kind of expression. When we linearize that, if we do a Newton linearization, then the Jacobian has this extra structure. So it has the original eta that's just evaluated at the point we linearize around. And then it's got this other term, the effect of which is to squash the conductivity tensor, kind of make it pancake-shaped, pointing in the direction grad U. So that introduces anisotropy. It ends up making the linear solves quite a bit more challenging. There's a simple discretization here that you can play with. Oh, okay, I guess you can't see the cursor. I will stop pointing at anything with the cursor. So there's this example noted at the bottom that's in PETSC. You can pull that up in the recent PETSC release or in PETSC Dev and run some of the examples that I'll show later. The first step of all of this is to write the residual. We'll end up spending a lot of effort so for more advanced solvers, we'll spend a lot of effort in operations related to matrices or related to multigrid, but the first step should always be to write the residual. And that should be very comforting because you write it once, you'll verify on small problems that the residual was coded correctly, and then you never need to worry about correctness. So we can write the residual and not write anything else. And then we'll go we can use a nonlinear method, or we can use a linearized method, but give this option -SNESMF. And this is a PETSC option. Other packages have something similar. And that means to do a matrix-free method with no preconditioning. And I have a couple other flags here to monitor the convergence. So you can see, for example, this number of iterations. It converges very quickly because this is actually a linear problem, so it'll always converge in 1 or 2 iterations. And we see here, as we refine, the number of iterations is basically going to double. So every refinement is doubling the resolution, and the number of iterations then approximately doubles, and approximately doubles again. And this is a really common feature. We'll see it all over the place. And this is part of why we need scalable solvers. So there's some other directions that we can experiment. So we can start using a preconditioner. So the default preconditioner, if we've assembled, so suppose that we've done more work now so that we can assemble the Jacobian, we can look at, say, an additive Schwartz method, which will use some overlap. It's still going to be running as a preconditioner for that Krylov method. We can do an algebraic multigrid. We can look at what happens if we didn't code up the true Jacobian, if we only coded up the Picard linearization. This is actually a common thing to do because writing the code for the Newton linearization is often reasonably challenging. So if we choose a Picard linearization, we can then do, say, a direct solver. We'll look at how that converges, and we'll see that it doesn't converge quadratically. It'll converge linearly. As an alternative, we can do this SNESMF operator. That's going to mean that we apply the action of the Jacobian matrix-free using finite differencing. This requires nothing more than the residual evaluation. And then we'll precondition it using this Picard linearization and, say, algebraic multigrid from ML. And we'll see that that does converge quadratically. So as we turn on any of the nonlinearities, that will still converge quadratically, which is a very attractive feature. And it's much less expensive because the Picard linearization doesn't have nearly as many non-zeros. We could also do more exotic things like nonlinear GMRes with a nonlinear preconditioner. And actually that option spills off the screen. Sorry about that. So there's a couple barriers that we should be aware of. First, the iteration count is basically going to scale like the square root of the condition number. So if we look at an elliptic problem, the classical elliptic ill conditioning goes like the mesh size h to the -2. So if we look at the iteration count, that's looking like 1 over h now, which is like the distance across the domain. So that's clearly we can't do any better than that without somehow providing global information flow or long-range information flow. The reason for that is the solution is globally coupled. So if we load the PDE over at one edge of the domain, we have to communicate that information all the way across to the other edge because it really changes the solution over there. And if our operator only moves the information one grid cell, we have to apply the operator as many times as it takes to move that information all the way across the domain. There's no way to beat that. If we have a preconditioner, then in principle we can move information much faster. The problem is that the classical preconditioners don't move information effectively enough, and so they don't fix that original elliptical conditioning. A one-level domain decomposition method gets you a little bit of the way. It sort of allows you to replace that little h with a big H, which is like a subdomain size. So the best possible would be to move information a full subdomain and not have any other terms. In practice, you have some other dependence on the ratio between the subdomains and the elements. And so that phi is at least logarithmic or polylogarithmic, and often it's some power. With multigrid methods, we can come out with a condition number that's of order 1. It's totally independent of the resolution. So we can do that with algebraic multigrid or with geometric multigrid. Now, the other challenge that we have is heterogeneity. So this is some kind of roughness in coefficients, or it may come out of the nonlinearity in the equations. So there, the conditioning is also proportional to the maximum material contrast. So fortunately, it's possible to locally correct that. So the local preconditioner can get us back to just the original elliptical conditioning. Unfortunately, representation on the coarse scales becomes more complicated because we have to still be able to accurately represent the long-range coupling. Now, often very fine grids end up becoming necessary because of the heterogeneity, and in that case, the original elliptical conditioning is still a major problem, and our coarse grids are now much more difficult to design because the fine scales were very rough. So this is a major challenge in implicit solvers. There's a few successful methodologies there, of which probably the most popular are the algebraic multigrid methods. So now we'll look a little bit at troubleshooting and a little visualization of what this ends up looking like. So here we take a pretty small problem. This is elasticity. There's two fairly rigid blocks. So those are in the upper left and the lower right. And we're visualizing the lowest 4 eigenmodes. These are the 4 plots here on the left side of the screen. And then on the right, we're visualizing the eigenvalues of that operator. So first we look at the original operator. There's no preconditioner. The stiff blocks basically don't move. And their associated eigenvalues are very, very small. This is like 10 to the minus 5. So that's a very ill-conditioned operator. We see on the right in the scale that there's no way you can read here. The right end of that scale is of order 1. It's the far left end. We have these eigenvalues that get very close to 0. So now what does a local preconditioner do? We can apply Jacobi preconditioning. This is the simplest kind of local method. And this basically balances out the stiffness. It recovers our traditional elliptical conditioning. We basically don't see those blocks anymore. They're not producing any sharp edges in these low modes. So that's great. The problem is it's going to end up being harder to go further. So we have a couple other methods. So we can apply an algebraic multigrid, and we look at what ends up getting missed by the algebraic multigrid. The fine grid smoother was correcting that, that roughness, and actually the way that the algebraic multigrid coarsens, it also it takes into account these interfaces, and it's actually doing an accurate job of representing the jumps and coefficients, except it's not doing an accurate job of representing the rotations. So if you look at the arrows on the left, this is where the two blocks rotate in the same direction, and then the one just to the right is where the blocks kind of tear. So where the two corners of the stiff blocks touch each other, they're rotating in opposite directions. So those are, if we were to remove those bottom two eigenvalues, our condition number would improve by like a factor of 5, because the next modes are not nearly as badly behaved. Anyway, the thing that's clearly missing here from the coarse grid are these rotations. It turns out it's not real natural to add those in the classical AMG. We can do it with geometric multigrid. We can also do it with smooth aggregation. But here, if we choose, say, geometric multigrid, but with Kalerkin coarse operators, then we look at these smallest modes, and the smallest eigenvalue here is 0.55, which is very good. On the last slide, the smallest was 0.08. So our smallest eigenvalue is like 0.55. They're fairly well clustered around 1. The vertical scale here on the eigenvalue plot is very stretched. They're all very close to 0 imaginary part. So this is a very nice performing solver. We'll get very fast convergence in all cases. If the Chebyshev smoother becomes a little bit unstable, so there's a tunable parameter in there, if you get too aggressive with that parameter, you end up with totally nonsense. So we've only adjusted the parameter a little bit, but it becomes unstable, and now these seemingly low energy modes are totally nonsense. So that's definitely broken. So what kind of convergence problems show up? What do we need to look at? So it's important to watch the true residual. There's a bunch of ways, say with a preconditioner being unstable, that it can look like we're converging if we look at the preconditioned residual, and we wouldn't be converging in the true residual. There's reasons why if the preconditioner is good, it's a little better to work in a preconditioned residual, but I'm not going to go into that in any detail here. So it's important to make whatever problem we're having as small as possible so that we can, and set it up in an environment that we can test rapidly. So we'd like to be able to iterate quickly and change parameters and see what's going on. So suppose that we've set that up. One of the first things to check is whether the boundary conditions are correct. If we mess up on the boundary conditions, the operator typically becomes singular. So we can check that by looking at an SVD or with a direct solver, which will usually choke if the system is singular. But maybe we had a system we knew was singular, but we know the null space. So a constant pressure mode is a common example of that. We can inform the solver about that. There's an interface for that, and the iteration will take into account the null space. It'll work out fine. Are the condition numbers reasonable? Some people come to us, they have, say an operator has condition number of 10 to the 15th. Well, we can't even evaluate a residual accurately. So we have no reason to expect that the solver will be any good. We can get an estimate of the condition number by this option, which will use the Krylov method to estimate to estimate the condition number, maximum, minimum singular values. The estimate of the lower singular value is very inaccurate, but as the iteration proceeds, we get some idea what's happening. So in GMRes, there's this restart parameter, and the restart can cause a lot of trouble. So using a long restart is a good debugging tool, although it's often not the most efficient way later. Sometimes we have a reason to use a nonlinear or inexact preconditioner. And in that case, we have to use a flexible outer method, otherwise we'll get nonsense. So for nonlinear problems, the most common mistake by far is that there's some error in assembling the Jacobian. So a very reliable thing to do is we can use this option SNES-MF operator, which will precondition with the thing that you assembled, but it will apply the action of the operator using finite differencing. And we see if that converges quadratically. We see if we see if the iteration count of the linear method, rather, should be 1, because those are effectively the same operator. They were supposed to be. That's a scalable way to test whether they're the same. And an alternative are these options to test or compare the explicit operator. That only works on smaller problems. So we have to assemble, we have to be able to assemble a dense operator to compare in general there. There's different ways of computing this parameter in the finite differencing. And this one, the SNES-MF type DS, is a method from Dennis and Schnabel. It's a more accurate but somewhat more expensive way to get that parameter. The other very common thing is that the linear solver is not accurate enough. So we should test by looking at the convergence of the linear solver, check that that's very accurate. Check that the linear system doesn't become singular. So we discussed those methods earlier. Is there some kind of bug in residual evaluation? That should be the first thing that we test. We can use manufactured solutions or benchmark solutions or whatever else, but we should be confident in the residual. Now, if the residual function is discontinuous, we have to be a lot more careful. So that's one of the things it should set off alarm bells if you know your residual function is discontinuous. And then there's a couple options here to like to monitor the line search, and using higher precision is also a good way to debug. Usually we don't do production runs with high precision, but it's great for debugging. Now, coupling approaches, which I'll go through fairly quickly. We can do coupling with a monolithic approach where we pile everything into like one big assembled matrix, for example, or one big multigrid iteration. Or we can do splitting. In the splitting, we assemble some systems separately, and we end up needing to understand global coupling strengths, but not necessarily all of these local issues. Which data structure is best depends on which method we use. So we want some generality. This slide actually comes from an ICE background, but you get the idea here where we incrementally add more and more models, and we don't want it to kind of upset all of our software. We'd like to be able to swap out these components and test pieces individually. So there's classical splittings based on relaxation. So that can be additive, like a block Jacobi. It can be a multiplicative, which looks like a block Gauss-Seidel, or there's symmetric variants of that. This kind of approach works well when the fields are loosely coupled. If the fields are tightly coupled, in the extreme case of tightly coupled is a saddle point problem like Stokes, then relaxation doesn't work at all because there isn't a lot of information on the diagonal. effectively. So we can do an approximate factorization based method. There we're going to have this nasty operator here, S, which is the Schur complement. The reason it's nasty is because it's dense, which means we can't form it. We have to deal with its structure, approximate its action or inverse without ever assembling it. And so almost all of the technical aspects of this class of methods is in approximating the Schur complement. I'm going to actually skip over a couple slides here on managing that in parallel. The basic idea here is that you have some global space. This is the space far on the left, and that's where you define the problem. And then there's other spaces that the solvers may work in. And what I usually recommend is that people write their assembly and all of their physics code in this space I call the split local space. So that's where you've separated out your major separate physics components, and you've communicated all the information needed, kind of ghost information, in order to compute a residual locally. If you use that, then we have an interface, which I'm describing here, for assembling the matrix that doesn't know anything about where the eventual solver will live. It doesn't need to create intermediate data structures. So on the Stokes problem, I'm going to run through a whole bunch of general approaches, which we can essentially do all using command line options. So there's block diagonal methods. There are, so in all of these methods, we can use algebraic multigrid. You'll see that showing up often to solve this viscous block. And then the off-diagonal blocks were the ones that were coupling with the pressure. And as we incrementally kind of add some more complexity here, most of it goes into the way that we approximate the Schur complement. Solving the other system is challenging, but it may be a little bit fewer choices. So a bunch of these are compared in various papers in the literature. We can also do a full factorization. This is a good debugging tool because this should be a direct solve. So we can also put this kind of structure into multigrid. We can have kind of multigrid on the outside instead of multigrid on the inside. And again, use a whole bunch of methods as smoothers now. Now smoothing for saddle point problems, the pressure doesn't have any self-coupling. That's kind of, the pressure block is the zero block on the bottom side there. And the pressure error modes aren't spectrally separated. So high frequency errors don't have any more energy than low frequency, and energy per se isn't really defined for the pressure. So not in the usual algebraic sense. So for smoothing, there are block smoothers. These are often the name Vanka is associated with those. There are methods that effectively amplify the energy of the fine grid modes, and this is what Aki Brandt calls distributive relaxation. And then there's the splitting methods that I was showing earlier, where we use some approximate Schur complement, often a diagonal approximation. And those are kind of most convenient for reusing code. The Vanka smoothers are based on relaxation of single element problems that involve the interfaces. So it's very tied to these staggered grid discretizations. You can do it with some finite element methods as well. Often you have like a piecewise constant pressure. You can bring all of the velocity degrees of freedom that touch that element and put that into a Vanka smoother, although the efficiency tends to not be as good as these very low order staggered grids. There's very good theory behind these. It's a very robust method. The distributive smoothing is based on trying to amplify the high frequency modes. And these have really nice theory for smooth problems without boundary conditions, but for rough problems, it's certainly not widely used. And then with split smoothers, we can very easily just reuse everything that we have, and these actually work fairly well. They're not quite spectrally right, but they work pretty decent in practice, often better than splitting on the outside. And I just have a couple more slides here on profiling basics. So I encourage people to get the math right first. You can waste a lot of time optimizing things and then find that you changed the algorithm and it was 10 times faster. So try to find something that is algorithmically the right kind of method. We want robust iteration counts. We want it to check that it really converges, so pay attention to the true residual, evaluate the errors. Once the math is right, then we play around with moving the time around. We look at where the bottlenecks are. So with PETSC, you can run with -log summary, and you can actually run with that and send it to our mailing list, and we'll give you feedback on it. But if you look at the norm and dot product operations, those basically measure network latency. That's the reduction, which on some machines is very slow. There's the map mult is measuring the neighbor exchange and memory bandwidth. It's often good to end up using unassembled matrices. I have a slide coming up on that. There's the time spent in the preconditioner in this PC apply. There's also a PC setup, which for algebraic multigrid or direct solvers, it tends to be very significant. The KSP solve is the total time spent in a linear solve. And then there's the couple of other operations that SNES does, the nonlinear solver. So the function evaluation and the Jacobian evaluation, those are user code. So, efficient, well-balanced solver, I would expect to spend, say, 30 or 40% of the time in function and Jacobian evaluation. If the solver is not really performing well, then we may spend lots more time inside of linear solvers, say. And that may tell us, hey, we should change our method a little bit. Say, put more effort into setup or do more things matrix-free. So we can compare the performance of an unassembled versus an assembled matrix. So here, the circles on this plot are just a conventional assembled system. This is in 3D with hexahedral elements as we increase the polynomial order looking to the right. I have two Y scales for this. On the left, it's the number of bytes that are transferred per scalar result. So I have some vector, I apply the operator, and I look at how many bytes were transferred divided by the number of entries in that vector. So with the assembled matrix, that grows in this, well, very quickly actually as we increase the order. The unassembled method uses a tensor product to evaluate to quadrature points, and then it looks like it's evaluating a residual at quadrature points, but in fact it's applying the linear operator. So it's the same kind of kernel that goes in, say, a usual finite element assembly or finite element residual. So that uses far less memory bandwidth. And the reason for this is that the coefficients at quadrature points are a very compressed and independent of the polynomial order way to represent the operator. The flops are not so clear, but memory bandwidth ends up being the bottleneck. And we see that. Oh, I have a question here. What's B, 1, 3, and 5? So B equals 1, so B is the block size. B equals 1 is a scalar problem. B equals 3 is like a like elasticity or the viscous block of Stokes, and b equals 5 is a, say, it would be like Euler equations, or say velocity, pressure, and temperature. So if we look at what hardware actually delivers to us, we get a lot of flops. So these operations, all the assembled matrix operations get a quarter or less than a quarter of a flop per byte that gets loaded from memory. This is because the entries just don't get used for very many things when we apply the operator. Whereas if we go unassembled, or we're doing residual evaluations, then we do a lot of flops locally. The hardware, meanwhile, is giving us like 8 flops per byte, and the expectation is that this trend will continue and the number of flops per byte keeps going up. So when we look at this, if, say, a double precision value can be computed in less than, say, 50 clock cycles, then we should recompute it instead of storing it. And that's what the unassembled methods are sort of doing, although they actually circumvent explicitly computing those entries at all, but they do more local work. That's good. Dave May has a bunch of results on this kind of thing in his multigrid Stokes solver. This slide, which I think is my last kind of solver slide, is looking at a Quasi-Newton method. So if we suppose it takes a lot of effort to assemble a Jacobian, or it takes a lot of effort to set up a preconditioner. If either of those things we want to amortize, then we have a couple different approaches. One, we can stay with a Newton type method, but we can start lagging the Jacobian. So now it's becoming a modified Newton method. And there we may struggle to converge because it's possible that the linear solver sends us in a direction that doesn't decrease the residual at all. And then the line search will kind of go haywire. And so the BT over on the very left is a backtracking line search, which is inexpensive, and the CP is a critical point line search, which is quite a bit more expensive but more robust. So within the conventional Newton methods, when we lag the Jacobian, so we have modified Newton, we end up doing a lot more work, and we're not decreasing this number of Jacobian evaluations very well. An alternative is a Jacobian-free Newton-Krelog, where we lag the preconditioner. So we apply the action of the operator with finite differencing, lag the preconditioner. The number of Newton iterations is going to be the same, or close to the same as the original method, but we don't have to set up don't have to assemble the Jacobian and set up the preconditioner nearly as much. The problem here is that the preconditioner becomes much less effective, and so we have lots of linear iterations. So the last note here, the Quasi-Newton or BFGS, is we use the old Jacobian as this seed for the BFGS algorithm, which is computing these low-rank corrections of the inverse. And this is a very effective way to lag. So if your Jacobian evaluation is expensive, or setup is expensive, we do that once. We find this is quite effective for elliptic problems. We set it up once, and then we go do BFGS with that in the background, maybe one B cycle, not even a solve, just put one B cycle in there. So we can see down at the very bottom here, the number of function evaluations has grown a bit compared to the original, but the number of Jacobian evaluations is now down to 2, and the total number of preconditioner applications, which is the number of linear iterations, is only 14, which we compare up to the top of the conventional method, which needed 31 linear iterations total. So this is a very effective way of amortizing that setup cost. So now we look a little bit at pipeline methods. So if all reduce is really slow, and this is true on a lot of clusters, it's true on most crays, it's not at all true on Blue Gene, which has really fast reductions across the whole machine. But this is a common bottleneck for Krylov methods as we go to large scale. And the solution that I advocate for that is to use pipelining. It uses this feature from MPI3 that's just now becoming available on these machines. It's essentially the same kind of algorithm, but in the background it lags the reductions so that they can happen concurrently with subsequent iterations. Another issue that comes up a lot is how to manage coarse grids in multigrid. So our algebraic multigrid packages manage this kind of thing, where they restrict the active set. But we need to think that the coarse levels, even when it's kind of being managed correctly, coarse levels can have a very similar cost to the finer levels. So the usual multigrid complexity goes out the window, and the cost for a V cycle may look like the number of levels. And in that case, aggressive coarsening becomes very important. Another alternative is additive multigrid, but this is not real popular because it's not as robust. And most software isn't set up to work that way, or not in the best possible way. So there's a couple packages. I'm a PETSC developer, of course, so I'll advocate that. You can go to our website. A lot of the same kinds of capability are in Trilinos. And when you design discretizations, think about what kind of solution algorithms you may want to use. There's a lot of choices you can put into a discretization that will make a solution algorithm really efficient. So that's a good thing to ponder at least a little bit up front, or to design in that flexibility. Learn how to evaluate the quality of a method, whether it's efficient, where the time is being spent, and experiment. There's a lot of choices. You're welcome to email our mailing list. And if you say, hey, I'm spending a lot of time doing these kind of things, here's some convergence results, here's a log summary, we'll probably have a good idea about how to shift things around to make that not be such a bottleneck. And finally, expect that the best method will change as you change your model setup and as you change the machine. So don't commit too heavily to one exact method. So that's it. Are there any questions now, or you can email?
Thanks, Jed, for that wonderful tour through solvers. While we have people typing in questions, I wanted to remind people that our next webinar will be actually on Valentine's Day, Thursday, Friday the 14th. For those of you guys aren't in a panic, getting your last-minute Valentine's Day in order. The talk will be by Sarah Minson on Bayesian earthquake modeling. So, questions out there? I don't see anybody typing. Oh, we got a typer.
So with the question here is about preconditioners for matrix-free methods. And you almost have to do multigrid in that case. So you can do local preconditioners like Jacobi and Gauss-Seidel, but those won't converge well. So you're almost required to do a geometric multigrid. You can do just one or two levels of geometric multigrid and then switch to an algebraic multigrid, and that's a fairly effective method. The matrix doesn't cost nearly as much on the coarser grids. But you're not likely to get anything automatic out of a matrix-free approach. Now, one thing that you certainly can do on a lot of problems is to simplify the system that needs an implicit solve. So there's a lot of systems where you have, say, many variables, but there's only, say, a scalar or maybe 3 variables that are coupled globally, so that represent the stiff timescale. So everything else evolves mostly locally, and then these variables are what transmits the long-range information fast. And those may not be explicit variables in the system, but sometimes they come out of perhaps a change of variables using an equation of state and then an approximate Schur complement. This is really common for stiff waves, which is not, so like in atmosphere at low Mach, or in a lot of magnetohydrodynamic applications. So in the case of stiff waves, often you can produce these reduced systems that are, say, scalar, and you can go solve those with a simple multigrid method. Whereas if you had stayed in the original variables without doing any approximate Schur complement business, then you would have had, say, a system that was transport dominated, which makes the coarse approximations more challenging, and that had many more variables that had to get incorporated in the coarse grids. So it's common to assemble some operators. It's so convenient for code reuse. It's so convenient for debugging to have the ability to assemble things. But the most efficient methods usually don't assemble the complete operator, perhaps pieces. Often in a matrix-free method, you'll assemble like a point block diagonal. So you apply the operator, you have this point block diagonal that you use in smoothing, and then you have coarse grids. Does that answer the question? Cool.
Thanks. Are there any other questions? For those of you who joined us late, and for those you want to share this talk with, this will be available on YouTube shortly. I will send out a notice on that. More questions? I don't see anybody typing. Jed, did you want to add anything else?
I'm just confused why no one has made fun of my mustache yet.
Then we will sign off, and thank you, Jed, once again for your participation, and everybody else for joining us today. And we will